Thank you all for joining this panel. This one is about benchmarking. So I wanted to start off in just a conversation about some of the limitations with our current standardized benchmarking, especially as it pertains to users. Different users have different application needs. They have different, say, like hardware configurations, access to hardware. So what are some of the trade-offs that come with, say, traditional standardized benchmarking? Oh, and also before we answer that question, you guys are free to give like a brief intro about yourselves and about the projects you represent.
Hi, so I'm Maya from StarkWare. This is my second panel today, so I guess you already know. What the limitations, I was actually just speaking about this, is that I think once you publish a benchmark, then people start to like hyper-tune to that, hyper-tailor to that benchmark. And then the benchmark becomes meaningless because people like tailor their prover to beat that benchmark instead of just making it good for all-around use. So yeah.
I'm Dmitry Khovratovich from Ethereum Foundation. So I'm a cryptographer, and from cryptography perspective, the benchmarking problem is very ambiguous. So generally, the problem is that, well, first of all, there is a lot of various hardware instances on which you can test and benchmark, and you can get completely different results. So even such a simplest thing as a hash function can be tested on 1,000 different machines, on different architecture from Raspberry Pi to GPU clusters, and you will have completely different results. Not only just plain performance, but relative ratios between how different hash functions compare to each other will also be different. For example, when SHA-3 function was selected, there was a very big benchmark instance called SuperCop, which enabled all hash function submitters to test their candidates on dozens of machines. And the truth is, you see these results, but you can't get any, it's very difficult to interpret them because anyone can choose a machine on which they are the best. On the other hand, anyone can choose the machine on which they are the worst. And depending, if you have 1,000 applications, each application may have its own instance, its own favorable hardware. So overall, it's very difficult to get like a single benchmarking number, which you can compare your design with others. So even with the cryptography schemes like hash functions, it's super difficult. Well, not super difficult, just difficult. But I'm afraid that with the zkVM things, it will be even more difficult because not only you can test it on very different hardware, but also you can run it with different parameters from security level to memory requirements. So for example, it may easily happen that your design have some kind of a computation memory trade-off or computation network trade-off, depending on how much network you can utilize, how much bandwidth you can utilize, how much memory you can utilize, and all this may prohibit you compare really apple to apples if you really want that.
Hello, everyone. My name is Alec. I'm with Nexus. And I would say for me, the limitation currently really lies in sort of domain-specific end-to-end benchmarks. You know, different real-world applications of zk definitely require different sort of evaluation metrics and prioritize different metrics, whether it's security, post-quantum security, latency, etc. So I think coming up with different domain-specific benchmarking that is standardized will be very critical.
Hi, everyone. I'm Norbert from zkCloud. Yeah, to be honest with you, it's, as we already see, we have 25-ish zkVMs currently out there and counting. So basically, to get a glimpse of the overall landscape for anyone who is looking to explore, like, which zkVM should I use, is super hard. And because of that, I mean, with all the, we don't have, and I don't think we have proper ways to do the benchmarking as of now. There are some good initiatives, including Ethproofs, for example. But like, I do find it very important to find some common ground and some common denominators in how we do benchmarking. For example, I'd say for someone to get an overall glimpse of where the landscape stands, I guess benchmarking on identical hardware and same workloads. And this can be different types of workloads. For example, how the zk benchmark website, I think the Lambda team is managing that. They use Kecheck, they use Fibonacci, and they use Ethereum block proving. So it's a kind of like a variegated set of workloads run on some machines. And I think it's very important, even though it may not reflect actual real-world complexity in full. With Ethereum block proving, partially yes. But like, I think it's very important. And then on top of that, if there are certain use cases that want to optimize for some specific thing, some specific aspect, then another type of benchmarking, for example, relying on what is the best performance capability of a zkVM with the most optimal setup they can get on some specific workload. That could be another angle to help users see a general overview with apple-to-apple comparison, and then specifically for their use case, find the best one. It's not easy because we've seen, I think we've all seen some kind of benchmarking wars in the past 2 years where teams indeed, as you mentioned, can just take the most optimal setup for yourself, show incredible results, take another, like the same setup may be very not optimal for another zkVM and say, hey, we are 10x, 50x, whatever, better than the other. So we do need objective benchmarks, I guess, and some common ground there.
So actually, it's good that you said that, because we actually, for Stu, because we saw the same exact thing that you're talking about, we commissioned an external team to standardize the benchmarks for us. I hope it'll be released this week or next week. So currently the tasks that we chose to benchmark are obviously Fibonacci, but SHA-2, SHA-2 chain, SHA-3, SHA-3 chain, and matrix multiplication, just code. So, and we fixed the hardware and we fixed the security bits, and we tried to make it as apples to apples as possible. We have an even deeper problem with benchmarking because our provers 2 proves, well, it's a general prover, but we have a Cairo implementation, like a Cairo errors for Stu. So basically, we write code in Cairo, and then there's Rust code for the other most other provers, and then you have to get into whether, well, maybe we cheated a bit when we implemented Cairo, made it better than the Rust implementation or something like that. So we benchmarked our prover on Cairo code versus Rust code on other provers, but also versus the precompiles on other provers without a precompile. So to show that we beat SP1, we beat RISC-0 with Cairo code versus precompiles. So, yeah.
Okay, great. So it sounds like some of the main limitations we're seeing, Maya, you mentioned about kind of different projects trying to hyper optimize based on, say, some of the optimizations that they compared to with other projects. And then Dmitry, you mentioned about kind of the diversity in the different types of hardware. Maybe some kinds of tasks has more kind of favorable hardware configurations. And then from over here, we hear from Alec about domain-specific benchmarking, and also Norbert about benchmarking from different use cases and about the diversity about the different tasks as well, which is an important component. And then I also wanted to ask you all about some of the properties that we should prioritize while benchmarking. So, but both you, Alec, and then also I believe Dmitry mentioned about potentially also security properties. Like right now, a lot of the benchmarking methodologies really prioritize on, say, efficiency-related benchmarks relating to speed or on latency. But what other properties should we prioritize, like, say, those relating to security? You mentioned, Alec, post-quantum security, for example, or maybe some about resource utilization, memory management, efficiency. So what are some of the properties that we should really consider when we're thinking about benchmarking?
So obviously, I think you should benchmark, you should fix some things and then benchmark all other things. Yeah, so you choose what you fix. Ideally, you find some neutral ground on hardware and security bits and things like this. And then you benchmark the proving time, the proof size, the verification time, because that's super important. Because like for instance, our prover is optimized for fast prover now, fast proving at the expense of verification time. So it's not like, so you really have to benchmark all, like the peak memory consumption. A lot of the provers, when you, like, for instance, we see the Jolt prover doing very well in certain tests, but it runs out of memory on the same hardware that other provers that are slower don't. So I think that's important.
Yeah, in this sense, that's just taking verifier speed is not sufficient, because there can be easily prover-verifier trade-off, so that you can, for example, have a more expensive prover at the cost of faster verifier or smaller proof. And it just may not be easy to compare apple to apples here. So one possibility is to have for benchmark, like something an upper bound for prover running on certain hardware. So it's not a guarantee that that all the provers run more or less on the same machine, but at least put them in more or less the same category. For example, prover using not more than 10 GPU instances and no more than several gigabytes of RAM, something like this, and then how much, and proof size at most, I don't know, 500K or something like this. And then you compare the verification time. And of course, you may have several instances of this. So it might be better to explore a trade-off, because, for example, right now, you may need shorter proofs, but maybe you can afford longer verification time. In the future, it can be all the way around. Like you can afford bigger proofs, but you need faster verification because you reduce the slot duration. So
yeah, I totally agree. And I think, just to reiterate, it will really come down to sort of coming up with different benchmarking standards with, different set benchmarks and fixed points for different applications. I think also something that still is a little ambiguous is sort of privacy capacity of different zkVMs, and how much information is kept secret.
Yeah, I think you guys said it all already, but maybe one thing I would add from my side, I really find it important that these things are open source, and like the entire implementations, the zkVM, and also, for example, multi-GPU orchestrators that are being used to show certain numbers. So yeah, I think I'd mention that. And also, obviously, audits, formal specs, formal verification later on, all these add up to those properties that could be investigated when trying to compare zkVMs.
Yeah, and that's a really great point that you mentioned, Norbert, about the open source and how important it is to provide that sort of transparency for other teams to see, other users to see, and also really appreciate the points about kind of tailoring the benchmarks, or like providing different standards based on trade-offs that different teams are willing to make as well. Like say you mentioned, Dmitry, about trade-offs, say, between verification time versus the proof size. Different teams may have different priorities, different users may have different priorities. So really important to try to like navigate through that plane. And on the topic of properties, I wanted to dive a bit deeper into the security property specifically, on Ethproofs right now. Within the pizza, I believe 6 out of the 8 properties are security related. So I'm wondering how we can go about with effectively assessing like evaluations with security, how, say, formal verification and audits can tie into it. So basically how we can like quantitatively assess the security side.
I'll go first again. So I think there's things that are easy and things that are hard. Like fixing the number of security bits is easy. Like the proof of work aspect of certain proofers, that's easy. Human error is always the hardest thing to quantify, obviously. Formal verification is important. We write lean proofs for all our errors. Audits, external audits. Obviously, open source audit reports after fixing any bugs that come up. Yeah.
Yeah, this pizza slices as Ethproofs are actually very, very attractive, but just the number, for example, 128 bits, it doesn't kind of show everything. In particular, when we talk about security in cryptography, the major part is to state all the assumptions that your system relies on. So, and it's actually not trivial for a big, complicated cryptography protocol to list all the assumptions that it relies upon. So here you have, even in the case of Starks, you don't have only the assumptions on the security of some conjecture, but you also have assumptions on the security of hash functions. And while these assumptions can be right or wrong, they can turn out to be wrong in the future, or there can be assumptions about uniformity of some functions, and overall there can be zkVMs that use sort of minimal set of assumptions, something that more trusted. Some of them use a bigger set of assumptions. Some of them using a set of assumptions that is, for example, minimum but are very novel and not really battle tested. So it's not easy to compare them, like again, apples to apples, because well, some of the assumptions they only kind of, we believe that they hold only after a sufficient amount of public scrutiny. Like again, with the security of hash functions, you cannot prove that a certain hash function is secure with very few exceptions, but you can only demonstrate that kind of dozens of cryptanalysts across the world have tried to break it and they failed, and this gives us confidence that this particular hash function is secure. And this kind of assumptions turn out to be true. We believe that they hold only after sufficient amount of public scrutiny. So when we list, even for benchmarking, when we list the security that we claim, there should be not only just number of security bits that we claim, but also all the assumptions that we rely upon. And there should be, of course, separate proofs that demonstrate, that reduce the security of the entire protocol to this particular assumptions. And also you mentioned security audits. So just the fact of audits is also not often sufficient. So I also do regular cryptographic and code audits with another team outside of the EF. And we certainly know that a project, it's not like black and white. So your project is audit or not audit, because the quality of the code may be so low that it's not easy to say if the code is secure enough. So like even after you run kind of 5 independent audits, still the code may be so optimized, for example, so optimized, and because of that obfuscated, that you don't confidently say that it's secure. It may require too much time from auditors to be confident, and still they are not as confident as with some kind of smaller, more compact and easily auditable code. So one parameter that we probably should consider is in general kind of auditability and readability of everything from the code to the mathematical specification.
Yeah, I think that would be a nice addition to open sourcing different zkVMs or different components, and then having a sort of metric, like you said, to evaluate that. I would also add that from my perspective, it's certainly difficult to sort of standardize benchmarking of key security assumptions, like you mentioned, in the trusted setup for different zk snarks and such. And so either figuring out some standard benchmarking for that or some kind of scoring mechanism, and encouraging sort of a movement towards more transparent, trusted, transparent setup environments would be more positive for security.
From my side, maybe I would add, I really like the pizza, the Ethproofs pizza for the zkVMs. I'd maybe add, I mean, all these were really good points. So I think that pizza will be dynamic, I guess, in the future. So as soon as certain part of the code is updated in the zkVMs, new precompiles are added, whatever, the delta there has to be, so that should be reflected in the pizza. Maybe it was green, it becomes yellow or orange or whatever that other color is. And until the delta is audited and verified as secure, it's becoming orange. And like this type of dynamism, I think, should definitely be there. Also, another, maybe a slightly controversial angle is like, so in the past year or two, we've seen 3, 4, or even larger X of improvement per quarter from many of the zkVMs. And like with this pace of the zkVMs changing, it's very hard for me to grasp when is a point when there is some kind of code freeze that could, sufficiently, like there is an audit on top of that and then sufficient confidence that it's secure. The pace has been so huge, it's just enormous. And then another thing is and this is the controversial part, is the go-to-market. Like these teams want others to use the zkVMs. Obviously, others want secure zkVMs. So like, what's the balance? Audits or even formal verification takes time. It's expensive. It's a very complex matrix that drives all these efforts.
Absolutely. And just on the topic of avoiding the apples to orange comparisons, which we touched upon briefly before. So for example, for zkVMs that may have some acceleration techniques, like if they say use proof recursion or parallelization, maybe some other techniques that really help boost the efficiency, should they be evaluated under the same configured baseline as some other zkVMs who say don't offer these properties? A lot of the times in, say, academic settings, these specifications would be normalized and say one system offers a feature, but the other system, which it's comparing to, does not offer the same feature. So in that benchmark, that feature won't be considered because like not all the systems that are being evaluated have that, versus say like industry-wide benchmarks where the best like performant case is considered across these different systems. How can we best evaluate these different scenarios in which we have, say, like different features across different zkVMs, and while avoiding these apples to oranges comparisons?
Well, one way to go is, of course, to ask designers of zkVM to suggest just a small subset of instances. Like, okay, instance 1 has this functions, instance 2 has this ones, instance 3 is has everything, and this sort of limits the number of benchmark values that we obtain. And if someone is particularly interested, that you can run this system on tons of other configurations, but they're not part of official benchmarks. So this will kind of throw the ball to the designers, because they will have to choose which functions they value more and suggest them for public scrutiny. That's one.
So I agree. I also think that we have the good fortune to not be in the academic paper setting, to have everything have to be contained in a single 12-page paper which is well formatted. So you can have, and we can see that you can have different benchmarking sites that benchmark for different settings. Like in the web, on mobile, for ETH blocks. It doesn't really matter because like a wealth of different standards will definitely just push everyone forward. So okay, if you don't have a GPU implementation for your prover yet, that's fine. You can be benchmarked for CPU, and other provers that do have GPU support can be benchmarked against each other for that, and recursion as well. Like you can have different options for different provers. You don't have to just choose one.
Yeah, I definitely think because of the rate of innovation and differentiation that's happening, we'll start to see, and obviously wanting to avoid just creating more and more benchmarks for every different type of proving system or zkVM. We're going to start to see sort of a slowly growing cohort of benchmarks for different design principles, perhaps with teams that are developing these, recursion-based proof systems and more innovative new sort of products coming up with their own benchmarks that then become more widely adopted. But I think that's a problem that we're all going to have to sort of work on together and sort of drive the development of more and more benchmarks as more and more proving systems are created.
Thanks. I think, Maya, you mentioned about Stu that you were even comparing the performance of Stu to the performance of RISC-V zkVMs with precompiles. And so it's kind of like, it seems apple to oranges, but for me, I think that's a very good example where you take a certain workload and you show your best capability. And I think here, in this case, the workload itself and that being uniform across all is the common denominator or the common basis off of which we can create comparability. I think one important thing here is, though, that when we do this and teams are allowed to use any optimal hardware, like any hardware most optimal for them, that hardware setup should be openly disclosed, and probably the cost of proof for that workload should also be openly disclosed as well. Because when we talk about real-time proving, for example, and succinct says 94% or 94% of blocks are now real-time proven, and there is a capability for that, while for RISC-0 it's something like 60%. But 200 GPUs versus that succinct mentioned for real-time proving constantly and every block, and like a cluster of 120K that RISC-0 mentioned, there is like an 8-10x difference there. So like even if we take a simple workload and identical workload and let any zkVM jump on that and do benchmarks on that, the cluster itself that it's capable to do some performance on is super important. So, and it's hard. I mean, at that point, it's hard to give it to a third party. So, I mean, but I do believe third-party type of standard hardware, standard workload type of comparison is also needed, but it may just limit our glimpse into what the actual zkVMs are really capable of.
You can normalize per dollar, right?
Amazon dollar.
Yeah, Amazon dollar, or Google dollar, whatever, yeah.
Yeah, but like, that's a good point, like Amazon dollar and normalize off of that. But like, the blockchain space itself is very good at finding the cheapest resource for whatever you need, the cheapest resource, electricity for BTC mining or, whatever. So it's like, is it really like comparing based off of Amazon instances a real comparison? Yeah, I'm not sure.
So we talked about kind of these apples to oranges comparisons. We also talked about properties that we should prioritize, some limitations. Now I want to go into the types of tasks that you believe should be benchmarked. So maybe Maya, since you mentioned about like StarkWare's recent benchmarking, maybe you can like walk us through the decision-making process for evaluating these tasks. And I remember, Norbert, you mentioned that kind of the diversity of these tasks, like for example, there was the Fibonacci sequence proving, and then also the mainnet block, and then the Keccak hash function. like kind of having that diversity of different tasks. But was wondering if we should really prioritize these real world use cases, like say with proving a mainnet block versus proving like different individualized operations, or even like simple program logic. Like some people really argue against having proving the Fibonacci sequence computation as a benchmark, even though that's very much like in a lot of benchmarking reports, that's something that a lot of people consider. But some other people think that we shouldn't include that because it doesn't really demonstrate any kinds of like real world use cases that users would like think that's useful for. So what are some of the different in terms of walking through the decision-making process, the types of tasks we should prioritize when looking at benchmarking?
Well, I think, first of all, this is a hard question, yeah. I don't claim to have a complete answer to it. It comes back to like whether you want to normalize to even the playing field, or whether you want to maybe care about more complex nuances. So yeah, we picked some tasks that we thought are important. We also wanted something that is so general that it's used by everything in the world, like matrix multiplication, just to showcase like a general use case for proving. But I think ultimately the only way that you know if a zkVM is right for you is by running it on what you actually want to do in the end. So for instance, we tailor our provers and our proving system to the StarkNet blockchain. We're now branching out to enable outside users to use it for client-side applications. But everything we did, our errors, for instance, are not as optimal as they can be, just to accommodate the fact that StarkNet currently operates over a large field, even though S2 is tailored for a small field. So it's kind of like you can benchmark everything, but ultimately you have to actually try the thing that you actually want to go for to understand what works for you, because you can't look at all of these tiny tasks and probably gather a big picture of how, like, ultimately how something will perform, currently at least.
I've just got an idea that, the real-time proving that we have been talking about is actually opening another security property that kind of implicitly should hold that all the blocks that appear in Ethereum should be proven in real time. And actually, it may happen that one will be able to craft a block that is totally fine from the plain executor, but terribly difficult for a prover, and terribly difficult not just in the computation amount, because probably it can be parallelized, but in terms of latency. So what if someone is able to craft a block that is so worst case that is just getting proven for 1 minute, and not for one proof system, but for many? This can be like a denial of service attack, that something resembling an attack happening several years ago, right? When there was an attack when an adversary was able to tamper with different parts of the Ethereum state all around, so that like technically it was cheap on gas, but computationally it was very expensive for clients. And here we have a new generation of clients. We have zkVMs, and for them new attack vectors open if they claim that they are real-time proven.
I'll take it back a little bit higher level and say that, to me, I think a lot of the sort of synthetic benchmarking methodologies like the Fibonacci sequence, etc., are very useful for sort of optimizing your current zkVMs, whether it's the hardware, the prover, etc. Whereas, like we mentioned, in order to integrate these a bit deeper into real-world applications, and really, like you said, you only really know if your zkVM is right for your specific task by running that task. I wonder if we can create a sort of derivative layer of benchmarks that are relatively simple tasks that are, whether domain specific to healthcare, and then sort of optimize for those different, whether it's security or privacy or verification speed or proving speed metrics needed for those different industries. So sort of looking again at the existing benchmarking methodologies as very much for optimization and improvement, and then having a new extended set of benchmarks for that implementation.
Maybe I do agree with everything you guys said. I think real-world workloads would be the way to go, because it's just like testing certain functions or certain operations, or like it may just be too abstract for an average application developer when they want to develop a zk app, and just they want to figure out which zkVM would be most suited. On the other hand, what I wanted to hint at, and that's something that our universal prover network is capable of. The functionality has been there in the DevNet since like the DevNet we launched last March, and then we've had another network launched in December, where it's not only us who can deploy provers there and start generating proofs, but basically it's a universal network, as in developers could take their prover binary and deploy it on the network themselves. So even if we have integrated RISC-0 and SP1, someone could take Stu and deploy their container and run their workloads with Stu using like the underlying hardware that's being utilized by provers on zkCloud. Now we've got pretty uniform hardware there because we apply random selection for assigning workloads in the network. And I don't want to talk too much about our setup, but what I want to hint at is that we need platforms that allow developers to not just test what's integrated by the developers of that platform, but that are open enough to allow me to bring my own customized zkVM, maybe where I made some optimizations. I throw it in there, and the prover network underlying the platform can actually generate proofs. And like it's like, how do I do self-benchmarking in a reliable way on a third-party provider's uniform hardware network, maybe, type of thing that I want to hint at. Hope I was able to express that properly.
Yeah, definitely agree with all the points here, and especially on that point of like the user-specific benchmarking. And Maya, how you mentioned, it's really hard to get like a big picture understanding with all of these kind of smaller tasks. And it's really up to the user using their own hardware configuration, figuring out what exactly they want to test it on their own. So really appreciate all the points that were made here on this panel, and yeah, lots of takeaways from this as well. So thank you so much for all of our panelists.